We propose multi-scale correlation searching homography estimation network, namely MCNet, an iterative deep homography estimation architecture. Homography estimation aims to find the projective relationship between two images, which is widely employed in various domains of computer vision and image processing tasks, including video stabilization, SLAM, planar object tracking, and so on. In this figure, we visualize the correlation at each iteration for the three correlation-based methods IHN and RHWF on the Google Map dataset. It is noticeable that although the correlations of IHN and RHWF continue to update during the iterative estimating process, the improvement is limited primarily due to insufficient feature resolution. Also, for all the homography estimation methods early proposed, the dynamic adjustment of loss for different samples has not been explored yet. We propose that samples with lower loss during the training stage can be allocated a larger backpropagation gradient to improve accuracy. The overall schematic diagram of our multi-scale correlation searching network is illustrated in this figure. MCNet takes the source image and target image as input and outputs the estimated homography matrix. The overall architecture includes multi-scale feature extraction and multi-scale correlation searching. MCNet conducts one-pass feature extraction for the entire estimation process. Subsequently, the extracted feature maps at different scales are used for multi-scale correlation searching. The iteration begins at the lowest resolution scale, with each scale running Q iterations. The core architecture of MCNet is the multi-scale correlation searching module. The estimated homography information in the previous iterations, which is carried by the translation of the four corner points of the image, is sent into the correlation searching module first. CS then conducts an iterative correlation search for Q times and then delivers the updated translation to the CS of the next scale, thus achieving iterative homography estimation through different scales. Different from previous methods that only employ the L1 loss for training, we introduce a novel fine-grained optimization loss, which collaborates with L1 loss to further boost estimation accuracy through introducing additional gradients in the convergence process of the model. As the single L1 loss of MCNet can reach a typically low value at the latter training process, we infer that the model enters a relatively stable capture range. At this stage, we expect the backward gradient of well-estimated samples to increase as the L1 loss further decreases. This selectively raises the weights of well-estimated samples based on the training accuracy and dynamically refines its impact during the training process to boost the estimating accuracy. Consequently, we design the FGO loss by employing an inverse proportional function. To reveal the effect of FGO loss, we train our MCNet using only L1 loss and evaluate it on the MCOCO test set. The computed FGO loss gradient, which is normalized for better illustration, is plotted in the left figure, showing that the model assigns larger backward gradients to more accurately estimated samples, thereby improving the estimating performance of the model while ensuring training stability. The zoomed-in result comparison of the original L1 loss and our FGO loss on MCOCO are illustrated in the right figure. It is observed that FGO loss achieves a significant improvement on the relatively accurate samples, increasing the fraction of the number of images of ACE less than 0.01 from 2.5% to 38.3%. We conduct evaluation on the MCOCO dataset, which is a widely used large-scale image dataset in computer vision tasks. And then, driven by the practical requirements for navigation and localization, we employ the challenging Google Earth and Google Map datasets to evaluate the performance under modality inconsistency. Finally, considering that real-world scenes commonly exhibit foreground occlusions that do not accord with the assumptions of homography, we conduct an evaluation on the SPID surveillance dataset, which contains dynamic objects and varying illumination. We list the ablation study of MCNet in the table. It is observed that raising the iteration can further produce more accurate homography estimation, with the side effect of a lower inference speed. We then compare the effectiveness of adopting the scale of a higher resolution under the fixed total iteration time of 6. It is observed that the addition of extra scales in our multi-scale correlation searching significantly improves the homography estimation accuracy while requiring negligible time consumption, which indicates the superiority of the multi-scale correlation searching framework of MCNet. We then conduct the ablation of the FGO loss, and we can see that the cooperation of our FGO loss significantly improves the estimation accuracy. Here we plot the ACE fraction figure comparing each algorithm on the four datasets. From MCOCO dataset, compared to the previous SOTA model, 2-scale RHWF, MCNet achieves a 20.5% reduction in MACE and a 31.6% improvement in the fraction of ACE values less than 0.01. Additionally, the proportion of ACE values less than 0.1 estimated by MCNet reaches nearly 100%, demonstrating the superior ability of our model. For cross-modal datasets, we observe that our MCNet outperforms the previous SOTA, 2-scale RHWF, by 43.4% and 41.1% in terms of MACE on Google Earth and Google Map, respectively. For dataset with dynamic foreground objects, MCNet outperforms all other competitors with a 47.1% reduction of the overall MACE compared to the previous SOTA model 2-scale IHN move. To further explore the performance of our network, we visualize the correlation of MCNet and IHN. In the visualization of correlation, the dark regions of the correlation visualization of MCNet cover most of the dynamic foreground objects, while the ones of IHN show limited ability to distinguish the foreground object. It indicates that the model has acquired the capability to better distinguish between foreground and background under our multi-scale correlation searching framework. For cross-modal datasets, as illustrated in this figure, our MCNet consistently achieves observably more precise estimation as the iteration continues, while the error reduction of 2-scale RHWF and 2-scale IHN generally becomes inconspicuous as the iteration grows. Although we adopt the multi-scale strategy into the correlation searching, we optimize each block in the framework to achieve notable efficiency, which can be observed from the first table. We compare MCNet with each algorithm in terms of inference time, flops, parameter cost, and memory cost. It is observed that compared to the previous SOTA Model 2 scale RHWF, our MCNet achieves a 20.5% lower mace while reducing the inference time, flops, parameter cost, and memory cost by a large margin. Under current settings, MCNet achieves an inference speed of 30.2 frames per second, indicating its potential in real-time accurate homography estimation. Those are all for MCNet, and thanks for watching.